All right, so let me finish this. I kind of ran out of the recording here for with Galileo. So again, he was called to Rome by the Inquisition. The you know the his book, of course, his works were banned by the Roman Catholic Church, and they forced him. And this is just the way things worked back during in the Middle Ages and certainly during the Renaissance. The Inquisition were just some horrible, horrible people. They would torture people and just do unspeakable things to them. And Galileo was well aware of that. Anybody um, who had any knowledge of the Inquisition knew that they would torture people. And so one of the things that they did with Galileo, they never actually tortured him. They just said, hey, if you better say that the heliocentric model, right? This where is it? I think I just passed it. Or the heliocentric model. Remember that goes against the church, according to because the church had adopted Ptolemy for some reason. They adopted the Ptolemaic model, which was the geocentric model, and to go against that was to go against the church, and so they said, look, Galileo, if you if you um, if you say that that's not true, that you are wrong publicly, then we won't torture you. And what they would do is they would show you the instruments that they were going to torture you with, and there was a very that was part of the procedure. And as soon as Galileo saw that stuff, he was like, no, no, thank you, I won't. I'm not going to put myself through torture. And so he was put under house arrest. I mean, he was he actually. I didn't tell you the entire story. Um, with his telescope, right? That he that the little one that he had invented. He actually made himself a very, very wealthy man. Plus, he wrote these very popular books, and so that was making him some money. And so he was put under house arrest. He had a really nice villa and he lived there for the rest of his life. Unfortunately, as I mentioned before, during the last 10 years of his life, he went completely blind. And we really do believe that was because he was making observations, unfiltered observations of the sunlight, even looking at the sun when it's close to the horizon, in the morning or in the evening, caused incredible damage to his retinas. So that was the life of Galileo. He's still, well remembered in physics and certainly in astronomy. All right. So as I mentioned before, for some bizarre reason, in the year 1642, Galileo passes away, and of course Isaac Newton was born. And they were, two very different individuals, but they both advanced science greatly. So Isaac Newton he was born in England, and in about the first 20 years of his life or so, um, you know, he had shown some evidence of mathematical ability, and he went to Cambridge, which is a very famous university in England, and he let's see, what year was that? There was a year that he what was it? It was, 1666. Okay, so it's the year 1666, and there's a plague here, let's see if there's a oh excuse me, go back to this. There's a plague, and in England, and just like unfortunately we had to do recently, um, in recent memory, the students were in danger, and they sent all the students home, and the students stayed home for about a year, I think. Um, and so when he went home, he had all this, he had just learned all this new mathematics, and and he knew about the physical laws of the universe, up to that point. But he himself started thinking about things, and he made incredible discoveries, particularly in mathematics, where he invented this thing called calculus, which is this unbelievable tool that allows us to really understand how the universe works. Of course, physics is the explanation for you. Physics and calculus go hand in hand, and so does astronomy, right? Astronomy uses mathematics and physics to explain what's going on in the heavens. This picture right here is a very famous picture of where Newton uses a prism uh, to break up sunlight into all the colors of the rainbow. Now he wasn't the first one to do this, but what he did is he broke up, he took sunlight, a little pinhole of sunlight, in a shade, and he passes, the light breaks up into all the colors of the rainbow, which again everybody knew about. I mean, not everybody, but people knew about that. But what he does is he takes another prism, and with that second prism, turns the colors of the rainbow back into, the white light of the sun. And that proves that the light of the sun is broken up into all the colors of the rainbow. So what he did, that was part of the physics that he did. It's called optics. He was one of the very first people to study optics. He also came up with the laws of motion. Remember, Kepler came up with the laws of planetary motion. He came up with the general laws of motion, very famously. And let's see. Let's see. He pioneered modern optics. Optics, not. He studied motion. He also studied gravity. All right. So remember going back to Kepler, a full generation or so before, Kepler thought that there was something that was holding the planets in their orbit around the sun, and Newton was the one that came up with the idea that it was gravity that did that. Let me explain that a little bit, because that certainly needs some explanation. Humans knew about gravity. It wasn't like suddenly Newton comes along and he realized that there was gravity. What Newton does is, people knew that gravity works when you drop a rock, for example, on the surface of the earth. It accelerates. That is, it moves faster and faster as it heads towards the ground. People knew that. I mean, that was not a big surprise. But what was surprising is this thing called gravity was actually a universal. It's a universal force, and Newton was the one to first work out the formula for that. And in fact, it's called universal gravitation. Isaac Newton's law of universal gravitation. And so that with that and his new calculus that he had just invented, you can work out the path of the planets. In fact, you can work out the path of any object orbiting another object. So remember, we talked before about here. Let's go back to it real quickly. Kepler's third law of planetary motion. Newton basically generalizes this so that here, let's get back to Newton. He generalizes it so he modifies the third law so that it is any object orbiting any other object, right? For Kepler, it's just things orbiting the sun. A cubed equals p squared for objects orbiting our sun. That's it. And so with Newton's modified version of that, you can work out what the mass of objects are, as well as just describing the how the period is related to the average distance. All right, so Newton's laws were the foundations of physics and astrophysics. It took about just more than 250 years for the beginning of the 20th century for anybody to start questioning Newton's laws of motion and gravitation, and those the theories they're still completely valid. I mean, we still use Newton's laws of motion and Newton's universal gravitation to go to planets and to send spacecraft to planets, to send people to the moon and back and things like that. But under extreme situations, Newton's laws of motion and Newton's universal gravitation break down. But of course, there was a person at the beginning of the 20th century who thought very deeply about this stuff, and his name was Albert Einstein. And Einstein came up with, of course, the theory of relativity. There's actually two theories of relativity. One of them deals with the motion of objects moving close to the speed of light. That's called the special theory of relativity. And so that basically fixes Newton's laws when you're moving close to the speed of light. And then he actually comes up with a completely new theory of gravity. Newton does. It's called the general theory of relativity. And you think of gravity no longer as a force, but as how massive objects curve the space and time around them. Right? So that's kind of what what Einstein does. So to kind of go off of what Newton had done, less than 100 years after Newton comes along, there's a guy named Herschel, another English guy, it turns out, that makes a discovery that nobody else made. He was using a pretty powerful telescope. That's the other thing. Newton actually says, "Hey, we could make a telescope using mirrors, like collecting light with a curved mirror, and that would be a better way of rather than just having all these heavy lenses, we'll use mirrors." And so Herschel, who again, we're talking about 100 years or so after Newton comes along, Herschel has this pretty good telescope and is the first one in modern time to discover a planet. And he called it Uranus, and then within within less than 100 years after Uranus, well, actually less than 50 years after Uranus is discovered, the motion of Uranus indicated that there must be something else out there. And so we actually used the theory of gravity, Newton's theory of gravity, to figure out the direction of this object. There was some object that was pulling Uranus in a kind of a strange way, and that mathematics led to the discovery of Neptune. Right. All right. So more. This idea of using mirrors is still what we use today. I mean, every modern telescope uses mirrors in some way. Even space telescopes use mirrors. All right, that's the end of the chapter. I'm going to do some examples